Hello everyone and welcome to the OneClass channel. My name is Donna and I'm a recent master's graduate from the Materials Science program from the University of Ontario Institute of Technology, also known as Ontario Tech University. So today we're going to go over some commonly asked questions in chemistry at the high school, college, and university level. So if you needed any help with homework or with tutoring, then check out the links in the description below. Now let's just get started on our set of questions for today's session. Okay, so question 1 asks, just to give the IUPAC names for the following compounds. Okay, so let's draw out all of the structures first. Maybe I'll just do like the first 3 so that we can just get the hang of it. But the first compound has a 6-membered ring, the carboxyl group, a double bond, and also a methyl group sticking out as well. Okay, so when I name compounds like this, I like to first number all of my carbons, starting with the most important group, which is this ketone. Let's number. In this case, I'm going to be numbering clockwise, since our double bond and our methyl group is on carbon 3, and we want to make sure we have the least amount of numbers in our final name. So instead of going from counterclockwise, I'll go clockwise so that it's only on carbon 3 instead of carbon 1, 2, 3, 5. Okay, so after I named all the carbons, I'll first write out the parent, which in this case is the ring itself. So when you name ringed compounds, you write cyclo, and then since there are 6 carbons in the ring, I'm going to put cyclohex. And first, I'll note the methyl group on carbon 3. So the prefix, I'll just write 3-methyl. Methyl cyclohex, and then from here I'll show where my double bond is. So it's also on carbon 3. So I'll just write 3 N. Since it's a double bond, you put N. If it was a triple bond, we put ein. And then lastly, I just have to show that there is a ketone on carbon 1. So I would just go 1 own. Okay, so this gives us the name 3-methyl cyclohex 3N1-one. Okay, so let's look at the second compound. Second compound has a carbon that has CH. So it has 1 hydrogen and 1 oxygen on one of its carbons. So that means this is an aldehyde. Let me draw it like this. And then the middle carbon has an alcohol. And then there is another alcohol at the end here. Okay, so they also showed some stereochemistry. Let me just fill that in. Okay, so first, again, I'm going to find my parent chain. So in this case, it is these 3 carbons. And then I'm also going to number it. So starting at the aldehyde, since that is the most important substituent on this chain. And now we just have to show which carbons have the alcohol groups. So in terms of stereochemistry, this is an R configuration. And then the carbons with the alcohol groups are carbon 2 and carbon 3. So I'm going to write 2, 3, di to signify there's 2 alcohols. And then hydroxy. And then propanal. Okay, so this compound ends in al. So this tells us that there's an aldehyde group. And notice that we don't have to say 1 al. It is just assumed that carbon 1 is the one that has the aldehyde. Okay, so this compound is R2,3-dihydroxypropanal. And now let's just do the last one. We'll just end it at part C. We have another cyclo group, methyl. Okay, so notice that we have a side group here that consists of 3 carbons, but it isn't like a straight 3 carbon chain. It's kind of in a different configuration. So typically we would only write propyl as the group, but since it is in this different configuration, this is called isopropyl. So it's still a 3 carbon chain, it just kind of looks more like a Y instead of a straight chain. Okay, so again, I'm just going to number this compound, starting with the aldehyde group, or ketone group, as 1, and then going clockwise. So let me write down the parent first. So similar to part A, this is cyclohex. And now I'm just going to show where all my side groups are. So on carbon 5, we have the isopropyl group. And then on carbon 2, we have a methyl group. I don't think I'll fit 2-methyl. And now I can write this cyclo X. And now again, I'm just going to show where my double bond is. So it's on carbon 2. So 2, N. And then on carbon 1 is our ketone. 1, one. Okay, so 5 isopropyl, 2 methyl, cyclohex 2, and 1 one. Okay, so now let's see what the junior tutor said. Aldehydes are named by replacing the terminal E of the corresponding alkane name with al. The parent chain must contain the CHO group, and the CHO carbon is numbered as carbon 1. For cyclic aldehydes, in which the carboxyl group is directly attached to a ring, the suffix carbaldehyde is used. Ketones are named by replacing the terminal E of the corresponding alkane name with -one. The parent chain is the longest one that includes the ketone group, and the numbering begins at the end near to the carbonyl compound. If other functional groups are present, the double-bonded oxygen is considered a substituent on a parent chain. The prefix oxo is used. Okay, so let's look at the 3 that we did. The junior tutor also got 3-methyl, cyclohex 3, and 1 one. For B, they got R, 2,3-dihydroxypropanol. C, 5 isopropyl, 2 methyl, cyclohex 2, and 1 one. And then the ones that we didn't do, for D, they started numbering the carbon at the first, going left to right. So they have 2-methyl, pentane, and then carbon 3 has the ketone, so they put 3 one. For the part E, they started numbering here. So you go 1, 2, 3, 4. So 3-hydroxybutanol. And then lastly, they have a benzene ring this time. And 1,4-dicarbaldehyde. So this shows that there are 2 aldehyde groups on carbons 1 and 4. Okay, so this solution is correct. Okay, so moving on to question 2. What would be the sequence for fluorine, lithium, beryllium, boron, and nitrogen in terms of increasing effective nuclear charge, Zeph, at n equals 2? Okay, so let's define what ZF means. So this is the effective nuclear charge. So, in other words, this is the net positive charge that is felt by an electron. So this is mainly because the nucleus is positively charged. So depending on where an electron is, like how close it is to the nucleus of an atom, it will feel a different nuclear charge than another electron. So that is ZF. If we were to have just Z, this is the actual nuclear charge. And I'll also define S, which is the number of shielding electrons. Okay, so the reason I wrote down all of these different definitions is because we'll be looking at how to calculate the effective nuclear charge. So it's simply the equation ZF is equal to Z minus S. So if we know the actual nuclear charge and we know the number of shielding electrons, then we can calculate ZF. So in the question n equals 2, so let me just write here, when n equals 2, the number of shielding electrons is also equal to 2. So S is also equal to 2 since it still just corresponds to the 1s electrons. Okay, so let's pretend we had like an atom. And then those are our 2 electrons. Okay, so basically we just need to look at all of the other Z nuclear charge values of fluorine, lithium, beryllium, boron, and nitrogen. So this depends on the number of protons that are in that element. And to find the number of protons, that is just the same as its atomic number. So starting with fluorine, it has an atomic number of 9. And then I'm just going to do its S is 2. So 9 minus 2 is 7. And then let's do the same for lithium. It has 3 protons minus 2, which is 1. And then for beryllium, its atomic number is 4. So its effective nuclear charge is 3. And then for boron, it is 5 minus 2, which is, oh, why did I say 4 minus 2 is 3? 4 minus 2 is 2. 5 minus 2 is 3. And then lastly, for nitrogen, it is 7 minus 2, which is 5. Okay, so now in terms of increasing nuclear charge, we can rank all of the different atoms. So starting with lithium as the lowest effective nuclear charge, and then beryllium, boron, nitrogen, and then fluorine. Okay, so this is because fluorine has the most number of protons, and when n equals 2, there's not much shielding, so that electron can feel that net positive charge. Okay, so the junior tutor said the actual nuclear charge, Z, is the net positive charge experienced by an electron in a multi-electron atom. In general, if an electron is further away from the nucleus, more atoms will be in between that electron and the nucleus. The electrons in between will cancel the positive charge of the nucleus and will thereby decrease the interaction between the nucleus and electron further away. As the electron is further away from the nucleus, it experiences an effective nuclear charge, which is less than the actual nuclear charge. This is called the shielding effect. If the distance r of an electron from the nucleus reaches to infinity, the effective nuclear charge will be equal to 1. If the distance r of an electron from the nucleus is 0, which means that the electron is very close to the nucleus and no other electrons will cause shielding effect, the effective nuclear charge is equal to the actual nuclear charge. Okay, so they have the formula Zeph equals Z minus S. For our question, we are asked to rank the given elements based on increasing effective nuclear charge. Since we defined that we want the effective nuclear charge at n equals 2, the value of S, which is the number of shielding electrons, will be equal to 2, since we know that the first shell always contains only 2 electrons. Z would be the actual net charges of each element, which is equal to its atomic number. And then computing for the individual Zeph of each element, we'll have 7, 1, 2, 3, and 5. Therefore, our final sequence in terms of increasing effective nuclear charge would be lithium, beryllium, boron, nitrogen, and fluorine. Yep, so the solution is correct. Okay, so on to question number 3. How does vapor pressure relate to intermolecular forces? Okay. So first, let's define what vapor pressure is. This is the pressure that is exerted by gas molecules. Okay, so let me just write down here. When you have stronger intermolecular forces, so the stronger the intermolecular forces, present between molecules, the lower the vapor pressure. And this is since the rate of evaporation lowers. Okay, so the junior tutor said, molecules of a liquid are in constant motion. With enough kinetic energy brought about by their molecular speeds, molecules may escape the liquid and become gas or vapors above the liquid. These gas molecules exert pressure called vapor pressure. However, the ability to escape the liquid is affected by the intermolecular forces between these molecules. Molecules that have hydrogen bonding has a lesser vapor pressure than those with only London forces and polarity. Yep, so that's pretty much the same thing as what I said, but I'll just also add my sentence as well to make it more broad. Okay, so on to question 4. For the oxidation reduction reaction equation given here, 2K plus F2 makes 2KF. Indicate how many electrons are transferred in the formation of one formula unit of product. Okay, so first let's just write down the reaction. And then just make sure everything is balanced. We have 2 potassium and 2 fluorines on each side. Okay, so now we just need to separate into its half reactions, so oxidation and reduction. So if we recall the acronym LEOGR, we can remember that losing electrons is oxidation and gaining electrons is reduction. And we can also look at whether or not the oxidation number is increased or decreased. So in the case of potassium, it starts off with an oxidation number of 0, and it ends up with an oxidation number of +1. So this means that the potassium was oxidized. In the case of the fluorine, it goes from an oxidation number of 0 to -1. So since its oxidation number decreased, we can see it got reduced. Okay, so now let's write out the oxidation reaction, which was 2K makes 2K plus 2 electrons. And in the case of the fluorine, F2 plus 2 electrons made 2F minus. So therefore, 2 electrons are transferred. So the reason we know that it's 2 is because since there's a coefficient of 2 in front of the potassium ion, then we need to neutralize this and add 2 electrons to our reactant side. In the case of the reduction reaction, we have 2 negatively charged fluorine ions, so we need to add 2 electrons to the reactant side to make sure that everything is balanced in that equation as well. Okay, so let's see what the junior tutor said. When a chemical reaction in a substance loses 1 or more electrons, it is called an oxidation reduction reaction. The substance which loses the electrons is said to be oxidized, and the substance which accepts it is referred to as reduced. The half reactions for this redox are 2K makes 2K plus 2 electrons, and F2 plus 2 electrons makes 2F minus. So 2 electrons are moved in the development of 1 equation unit of item. Yep, so the solution is correct. Okay, so now let's move on to question number 5. Which are the main monosubstituted derivatives of benzene? Okay, so first I'll just draw out benzene. It contains 6 carbons. In a cycle. Wait, I think I just drew 7. Hold on. Okay. And then in between each carbon, well, every other carbon is a double bond. And then since carbon needs 4 bonds in total, all of the carbons contain a single hydrogen. Okay, so this is benzene. So when we have a monosubstituted derivative, since there's a prefix of mono, this can help give us a hint of what this means. So monosubstituted means that one of the hydrogens is substituted with another functional group. So depending on the functional group, they'll all have different names, obviously. So I'll just write down some of the main examples, and then we can see what the junior tutor said. So I'll just simplify it and draw benzene like this. So if the benzene had a single methyl group, this is called toluene. If the benzene ring had like a chlorine group, this is chlorobenzene. And similarly, if the benzene had a bromine group, this is just called bromobenzene. So these halides are usually used in like organic reactions because they make for good leaving groups. So typically when you start off with bromobenzene, most of the time it gets replaced by a different side group of your choice. And I think I'll just write down one more. Let's say we had a benzene ring with an alcohol group. This is just called a phenol. Okay, so let's see what the junior tutor said. Benzene is an organic and hugely important chemical compound with the molecular formula C6H6. It consists of 6 carbon atoms joined together in a ring with a hydrogen atom bonded to each carbon. Many important chemical compounds are derived from benzene by replacing one or more of its hydrogen atoms with another functional group. The derivatives of benzene are classified into monosubstituted, disubstituted, trisubstituted, and polysubstituted. So monosubstituted derivatives are those in which one hydrogen atom is substituted with another functional group. The most common monosubstituted derivatives of benzene are, so this phenol I think was meant to go to the last one, toluene, chlorobenzene, and bromobenzene. So this is benzaldehyde. So everything's just a little out of place. Benzoic acid is the second one here. You can see it has a carboxylic acid group. And then aniline, I believe, is the one with the NH2. And styrene is the one with the double bond. Let me just Google. Yeah, so styrene's the one with the double bond. Benzonitrile, acetophenone, anisole, and nitrobenzene. So acetophenone is the second compound here. Benzonitrile is the last one. Nitrobenzene is the NO2 group. And anisole is that, yeah. So it's pretty much like methoxybenzene, so it's the third compound here. Okay, so the solution is correct. There's probably just the image just got a little shifted, so that's why all the names are kind of misplaced. But I'll still say the solution is correct. Okay, so for this question, they want us to identify the precipitate or lack thereof. So precipitate means like a solid is formed in the solution. So that means, in other words, it is not soluble. So let's start off by writing out the first reaction. We have NaCl plus barium hydroxide and we need to figure out whether or not these products are soluble or not. So I'm just going to leave them blank. And we are going to look up the solubility rules and how to use this table. Okay, so here is an example of what a solubility chart might look like. So basically it just gives you all the rules and also with some exceptions to the rules. So if you have a compound containing lithium, sodium, potassium, or ammonia, these are always soluble. So you can see here the NaCl is aqueous. So that means I can also write that our sodium hydroxide is aqueous as well. Moving down here, so we look at what pertains to the barium chloride. So compounds containing chlorine, bromine, and iodine are insoluble only with silver, mercury, and lead, and they're soluble with any other ion. So therefore I can write that barium chloride is also aqueous. Okay, so let's look at the second reaction. So there's no precipitate in the first one. And now let's look at the second reaction. Like they already wrote aqueous there, but I'll just double check on our chart. Okay, so in the case of the silver, if we go back to that same rule where compounds containing iodine are soluble, except when they are paired with silver, mercury, or lead. So then we can say that this precipitates. And in the case of the magnesium, I believe since it is a 2A ion, let's try to find a table that has it. I believe this compound is just soluble. Yeah. Since it's I'll just put aqueous. Okay, so therefore this is the precipitate. Okay, so let's see what the junior tutor said. Reaction 1, no precipitation. Reaction 2, it's the silver iodide. Explanation. When a substance is mixed with a solvent, there are several possible results. The determining factor for the result is the solubility of the substance, which is defined as the maximum possible concentration of the solute. Solubility rules help determine which substances are soluble and to what extent. It also helps in determining if there will be a precipitate in the products or none. Following are the most commonly used solubility rules. that can help predict whether a compound is soluble in water or not. Okay, so they just summed up all the rules. Salts containing group 1 elements like lithium, sodium, potassium, cesium, rubidium, all soluble, and salts containing the ammonium ion. With the nitrate ion and chlorides, okay, so they just said they are generally soluble. No exceptions. Salts containing chlorine, bromine, or iodine are generally soluble. Important exceptions to this rule are halide salts of silver, lead, and mercury. Most silver salts are insoluble. Okay. Most sulfate salts are soluble. And there are some exceptions as well. Most hydroxide salts are only slightly soluble. And the sulfides of all metals except barium, calcium, magnesium, sodium, potassium, and ammonium are insoluble in water. Carbonates are frequently insoluble. Chromates are frequently insoluble. Phosphates and fluorides are frequently insoluble. For the problem, number 1, rule number 3 confirms that barium chloride is soluble and will not precipitate as a solid, while rule number 1 states that sodium hydroxide will completely ionize, so there's no precipitate in reaction 1. For reaction 2, rule number 3 confirms that the silver iodide is insoluble and will precipitate in the solution. Rule number 2 states that all chlorides are soluble, which means that magnesium chlorate is soluble and will remain as an ionized particle. So in an item 2, there will be a precipitate in the form of silver iodide. Yep. So this solution is correct. Okay, so on to question number 7. Two different compounds exist having the formula N2F2. One compound is polar, whereas the other is nonpolar. Draw Lewis structures consistent with these observations. Okay, so when you write Lewis structures, I like to first try to find the total valence electrons of the compound. So in the case of N2F2, we have nitrogen, which has 5 valence electrons. And since there are 2 nitrogen atoms, 10. We multiply this by 2 and get 10. And for fluorine, each atom has 7 valence electrons, and there are 2 of them, so we have 14. And then if we add this together, we have a total of 24 valence electrons. So first, let's just write the 2 nitrogens. And I'll also show if the fluorines are on both sides, like on the same side. And now I'm just going to draw out all of my lone pairs on these terminal atoms. Okay, so if we count it out, we have 2 electrons in each bond. So I drew out 1, 2, 3, 4, 5, 6. And I also have 6 electrons as lone pairs on each of the fluorines, so I only have 12 so far. There as well. So we have 18 drawn in total. So I'm going to draw a double bond in between the 2 hydrogens, so that leaves us with 20. So I need to put 4 more electrons. So each nitrogen atom will have a lone pair. So that gives us the 24 valence electrons that we need. And you'll notice that I wrote this structure in the cis configuration, meaning that the fluorines are on the same side of the double bond. So if we remember that fluorine is way more electronegative, there's going to be a non-zero dipole moment going in the direction of the fluorines. So therefore, this compound is polar, since the dipole moments don't cancel each other out. If anything, they're more amplified. But if I were to draw the trans configuration of this molecule, so this means that each of the fluorine groups are on opposite sides of the double bond. So let me just show one up there and one down here. If I show the dipole moments of the fluorines, they go in opposite directions and they cancel each other out. So therefore, this molecule is nonpolar, since the dipole cancel each other out. Okay, so let's see what the junior tutor said. The nonpolar and polar Lewis structures of N2F2 are as follows. The cis isomers considered to be polar, two substituents are positioned on the same side. The two fluorine atoms cause two dipole moments that do not cancel each other, hence making the compounds polar. In the case of the trans isomer, two fluorine atoms are positioned on opposite sides, direction of the dipole moments cancel each other, and the resulting molecule is nonpolar. Yep, so this solution is correct. Okay, so on to question number 8. How is the boiling point of a substance defined? So this is the temperature where your liquid turns to vapor. Yeah, pretty much. I'll also just add, and when the vapor pressure of a liquid is equal to the pressure surrounding the liquid. And the junior tutor said the boiling point of a substance is defined as the temperature where the vapor pressure of the liquid is equal to the atmospheric pressure. Yep. So the solution is correct. Okay, so question 9 just says to write the electron configuration for carbon. So first I'll just look up the periodic table when it is separated into the different blocks. And if we find carbon, which is atomic number 6, we can try to write out the electron configuration. So starting from hydrogen and going from left to right, we have 1s2, and then the next row, 2s2, and then moving over to where the carbon is, it will just be 2p12. So yeah, that's pretty simple enough. And the junior tutor said, electron configuration of carbon, 1s2, 2s2, 2p2. Apply the off-bow building up principle in writing the electron configuration. An s orbital can house a maximum of 2 electrons, and a p orbital can hold a max of 6, and carbon has 6 electrons in total. Yep, so this solution is correct. Okay, so question 10. Which period of the periodic table A has no metals, B has no nonmetals, and C has 1 post-transition metal and 2 metalloids? Okay, so let's look at the periodic table given here. If we look at period 1, which only contains the hydrogen and helium, this has no metals, and the nonmetals are shown as green, and the blue is shown as metals. So only period 1 contains no metals whatsoever. So for A, I'll write down period 1. For B, which period has no nonmetals? So pretty much only metals. So we can say our lanthanides and actinides, or we can even just say period number 7. It's all light blue, so it has no nonmetals. And for C, has 1 post-transition metal and 2 metalloids. So the metalloids are in orange, and gallium is a post-transition metal. So I'm going to say period 4. And the 2 metalloids, uranium and arsenic. Okay, so the junior tutor said for a period that has no metals, it is period 1. Period that has no nonmetals, it is period 7, which is the 7th row. And then C, period 4. Yep, so this solution is correct. I think we have time for one more quick question. 11. Given the following single-step reaction, draw the curved arrow mechanism. So we start off with a bromine group plus this negatively charged oxygen. And even just looking at the product that is given, we can kind of guess what happens in the reaction. You can see that the bromine is replaced with the oxygen, and this is Br minus. So what happened was that this negatively charged oxygen came in and attacked the carbon containing the bromine, which kicks off the bromine so that it acts as a leaving group. So this is an example of a nucleophilic substitution reaction. And the junior tutor said, the reaction shown is a nucleophilic substitution reaction where the methoxy group replaces the bromo group in the alkyl halide. To draw the mechanism, we must know what kind of nucleophilic substitution reaction occurred. Most likely reaction would be SN2 since the substrate is a 1-degree alkyl halide with a strong leaving group bromine. Also, the methoxy ion is a strong leaving group. And the mechanism will occur as follows. Yep, so this solution is correct. Okay, so if you enjoyed today's Q&A and you'd like to be notified of when we do this next, then please hit the subscribe button and notification bell below. And if you'd like to submit a question of your own, then check out the links in the description. Also, if you liked today's video, you can leave it a like and a comment, and don't forget to share with your friends and classmates if they needed any help with chemistry. This has been Donna from OneClass, and I hope to see you soon. Bye.